Welcome to Neural Blockchain, a podcast where AI hosts explore a wide range of cryptographic and decentralized ledger topics, from ZK proofs and multisig to consensus mechanisms and scaling techniques. Your feedback would be greatly appreciated, and I hope you enjoy the following conversation.
Ever get that feeling where you really want to understand something, like what's making all these new blockchains tick, but the thought of wading through all that technical jargon makes your head spin.
I know exactly what you mean.
That's exactly what we're tackling in this deep dive. We're going to explore the world of blockchain consensus, but we're going to cut through the noise and give you the key takeaways.
That's right. We've gone through a ton of research analysis and really dug into the latest advancements in blockchain for this one.
Absolutely.
Our goal, well, it's pretty simple. We want to equip you with a clear understanding of what's driving this next generation of decentralized systems.
Exactly. And specifically, those mechanisms that allow these networks to agree basically on a single version of the truth.
Yeah, the heartbeat of it all.
Exactly, the heartbeat.
Now, we're not going to dwell on the basics like Bitcoin's proof of work or Ethereum's proof of stake, those foundational concepts.
Right. We're way past that.
We're going beyond those, diving into this sort of, you could call it a boom in innovation in how blockchains reach consensus.
A Cambrian explosion.
Exactly.
And this isn't just abstract tech talk, right?
Right.
Because as blockchain finds its way into more areas of our lives.
Exactly. Think about things like decentralized finance or DeFi, enterprise supply chain solutions, or even like securing data from billions of IoT devices.
Right.
Understanding these consensus mechanisms, well, it becomes like truly essential for anyone who wants to wrap their head around the future of this tech.
Absolutely. And it's about, understanding the trade-offs at the heart of these systems so that you can be well-informed about their potential and limitations.
That's the key.
So proof of work and proof of stake, those were like the first engines.
Yeah.
Now we're seeing this whole array of specialized high-performance designs emerging.
Absolutely.
One of the early evolutions was Delegated Proof of Stake, or DPoS.
DPoS, yeah.
And this is often presented as a more efficient and in some ways more democratic spin on traditional proof of stake. What's really interesting here is how transaction validation happens. Instead of potentially having every single token holder validating blocks, DPoS introduces this idea of an election.
It's a fascinating shift.
Token holders, they vote for a smaller set of delegates, often called witnesses or block producers.
Yeah.
And those guys take on the responsibility of verifying transactions and creating new blocks.
It's like moving towards a representative model.
Exactly. It's a blockchain-based republic. You, as a token holder, you vote for delegates you trust, and those elected individuals, they handle the day-to-day operations of the network.
Keeping things running.
Exactly. Validating transactions, keeping the chain moving. And our sources highlight that there's this mechanism for regular re-elections, keeping those delegates accountable, theoretically, to the token holders.
Right.
So the core insight here is that DPoS trades broader participation for faster speeds by electing these representatives. But of course, this introduces risks of centralization and voter apathy.
You've got it.
Now, if we look at why DPoS came about, a key driver was addressing those scalability bottlenecks of earlier blockchains.
Right.
By having a smaller, fixed number of validators, the network can process transactions much more quickly. Some DPoS-based blockchains, like EOS, they claim throughput in the thousands of transactions per second.
Yeah, a significant jump compared to the earlier generations.
Oh, absolutely. And because you don't have this massive global network constantly competing to solve those cryptographic puzzles, the energy consumption is also considerably lower than proof of work.
Much more energy efficient. That's a big plus.
A huge plus. And the sources also point out that DPoS incorporates a form of network governance, which is kind of cool. If token holders get unhappy with their delegates, how they're performing or their behavior, they can actually vote them out and elect new ones.
It's an interesting mechanism.
So it sounds pretty appealing on the surface. It's faster, greener, and there's this built-in accountability system. But we need to dig a little deeper because the sources also reach up some important considerations.
Absolutely. This leads us to a crucial trade-off, the potential concentration of power.
Right.
While the idea of electing delegates sounds democratic in theory, the reality can be, more complex.
For sure.
In practice, we see this tendency for validator cartels to form.
Like what does that look like?
Well, it's where a small, often well-resourced or strategically connected, group manages to get elected consistently. And this can create a situation where a relatively small number of entities control most of the block production.
Yeah, and that sort of undermines the whole principle of decentralization.
Right.
So if you've got a handful of big players controlling most of the elected delegates, the network becomes vulnerable, less resistant to things like censorship or manipulation.
It's a valid concern.
And then you have the issue of voter turnout. Just like in real-world elections, not every token holder actually participates in the voting process.
Voter apathy is a real challenge.
So if only a small fraction of token holders are voting, a small group could easily maintain their positions, even if the wider community wants something different.
Right.
So the will of the people, or I guess the token holders in this case, might not always be reflected in who gets elected and what decisions they make.
It's a point to consider. The sources highlight this challenge. We see it play out in networks like EOS, with its 21 elected block producers, Tron, with its 27 super representatives, and Lisk, with its 101 delegates.
Right.
While these systems can achieve high transaction throughput, that trade-off in terms of true decentralization is a significant factor.
So these DPoS systems, they're often favored for applications where high speed and lower fees are paramount. Things like decentralized applications or entertainment platforms.
Exactly, where those factors are key.
Okay, so with DPoS, we've got this model of elected representatives keeping the blockchain running, offering speed and efficiency, but with potential concerns around centralization. Let's shift gears to a completely different consensus mechanism, proof of authority, or PoA.
All right, PoA.
This one takes a very different approach to who gets to validate transactions.
It really does. PoA is fascinating because it moves away from the focus on stake, whether that's computational power or crypto holdings. Instead, it hinges on the identity and reputation of pre-approved validators.
It's less about who has the most coins and more about who's trustworthy, right?
Exactly. It's more like a private or consortium network where a select group of trusted entities are granted the authority to validate transactions.
Right, like a VIP club for validators.
You could say that. The key insight here is PoA prioritizes efficiency and trust in permission settings by leaning on the reputation of known validators. But it fundamentally sacrifices permissionless ideals.
Okay, so walk me through this. Who are these validators typically?
They're usually known organizations or individuals, established institutions, trusted business partners, or recognized experts. And they're essentially staking their real-world reputation.
So their credibility's on the line.
Exactly. If they act maliciously or irresponsibly, they risk serious damage to their public image and standing.
That's a pretty strong incentive to play by the rules.
Absolutely. Now, connecting this to specific needs, PoA offers some compelling advantages.
That's yes.
Well, because you've got a limited and well-defined set of validators, the network can achieve very high scalability, often reaching thousands of transactions per second.
Right. We see this with the XDAI chain, right?
Exactly. It also boasts incredibly low energy consumption and very fast transaction finality. You don't have the overhead of a large anonymous network trying to reach an agreement.
Which makes sense, right? You've got this small, trusted group efficiently processing transactions. But what's the trade-off?
The trade-off is clear. It's centralization by design. This is a permission system, not a permissionless one.
Right, so we're back to that trade-off again.
It raises a fundamental question about the core values of decentralization that many people associate with blockchain technology.
Right.
PoA inherently depends on the trustworthiness of a limited number of validators.
So what happens if those validators are compromised, either through malicious intent or external pressure?
That's the risk. Or if they collude with each other, the integrity of the entire network could be at risk.
So you gain efficiency and speed, but you give up a degree of decentralization and censorship resistance.
Precisely. It's a trade-off that makes sense for certain uses where knowing and trusting the participants is the primary concern, maybe even more so than absolute open decentralization.
Okay, so for example, the XDAI chain, which is focused on those stable and fast payments, VChain, which is used a lot for supply chain management and tracking, and even Ethereum test networks.
Right, those are all good examples.
These are often private or consortium blockchains or enterprise-level solutions where a high degree of trust already exists among the participants.
Exactly.
Okay, let's move on to a consensus mechanism that's specifically designed to work even when some participants might be deliberately trying to disrupt the network.
Okay.
It's called Practical Byzantine Fault Tolerance, or PBFT. Even the name sounds intense.
Yeah. It does have a certain ring to it, doesn't it?
It does. Byzantine Fault Tolerance.
The key insight here is PBFT excels at security and immediate finality, especially in smaller, trusted groups.
Oh.
It uses this robust voting system, but its communication overhead limits its scalability for large, open networks.
Right, so break this down for me. What exactly is a Byzantine fault?
Well, imagine a situation where network participants can behave in completely unpredictable and potentially malicious ways.
Oh, okay, like bad actors causing chaos.
Exactly. They might send false information or contradictory information to different parts of the network.
Like to disrupt things.
Exactly. And PBFT is designed to make sure the network can still reach a consistent agreement even when a certain number of participants are acting in this Byzantine manner.
So it's built to withstand those bad actors.
Precisely. And it achieves this resilience through a clever system. It involves a designated primary node and several backup nodes, and then this multi-round voting process among all the participating nodes.
Like a system of checks and balances.
Exactly. And the key is that the system can tolerate a certain fraction of faulty nodes. As long as less than 1/3 of the total network participants are Byzantine, the system can function correctly.
So it has built-in redundancy to handle those disruptions.
Precisely. The sources emphasize a significant advantage of PBFT for applications that need a high level of trust and immutability, immediate transaction finality.
So unlike some other mechanisms where there's a chance a transaction might be reversed, with PBFT, once a transaction is confirmed, it's final. There's no going back.
Exactly, no forking of the chain. And for networks with a relatively small number of validators, PBFT can also offer high transaction throughput.
Now, the sources mentioned a key limitation. Scalability.
Right. That's the challenge with PBFT.
Explain that.
The communication complexity between the nodes grows very rapidly with the number of participants. Imagine everyone in a room needing to have a direct conversation with every other person. As the room gets bigger, the number of conversations explodes.
It's chaotic fast.
Exactly. This communication overhead makes it tough to scale PBFT to very large, open networks.
So it works best with a smaller, known, and trusted set of participants.
Precisely. And typically, PBFT needs a way to verify the identity of the validators, which leans towards permissioned or consortium blockchain environments.
Where everyone knows each other.
Exactly. But in those settings, there's also a potential risk of censorship if enough validators collude.
So it's a powerful mechanism, but with its own set of trade-offs.
Absolutely.
We see PBFT being used in platforms like Hyperledger Fabric, which is popular for enterprise solutions.
Right.
Also, it's the core consensus engine behind Cosmos's Tendermint protocol, designed for building interoperable blockchains. And then you've got Zilliqa, which uses a hybrid approach incorporating PBFT.
Right.
These are all examples where security and the ability to handle faulty actors within a known group are really important.
Absolutely. Those are the use cases where PBFT shines.
All right, let's shift gears again. We've got PBFT giving us security and finality for smaller groups. Now let's look at a completely different way of structuring transaction data. Directed Acyclic Graphs, or DAGs.
DAGs. Interesting stuff.
This moves away from that traditional linear blockchain structure completely.
It's a different paradigm.
The core idea here is that DAGs offer the possibility of immense scalability by having transactions directly validate each other.
Right.
But their security models are still evolving, and early implementations faced some centralization challenges.
There are definitely trade-offs to consider.
So tell me more about how DAGs actually work.
So instead of a sequential chain of blocks, individual transactions in a DAG directly validate one or more previous transactions.
Okay.
It creates this web-like structure, a constantly branching and merging graph of confirmations.
So it's like a tangled web of transactions validating each other.
You got it. Imagine a decentralized ledger where new transactions add to and confirm older ones, rather than being bundled into blocks added to a chain.
Interesting. And the sources are pretty excited about the potential of DAGs.
And with good reason. Because you can validate multiple transactions concurrently, this architecture theoretically offers almost unlimited scalability.
So as network activity increases, more validations happen in parallel, leading to higher throughput.
Exactly. And some DAG-based cryptocurrencies, like Nano, even have fee-less transactions.
Which is a big deal for users making frequent small transactions.
Absolutely. It's a game changer for things like microtransactions in the Internet of Things, where billions of devices might be exchanging tiny amounts of data or value.
So lots of potential there.
Huge potential. However, the sources caution that security models for DAGs are often more complex and are still under development development compared to traditional blockchains.
So there's still work to be done on the security front.
Absolutely. And early DAG implementations, most notably IOTA, relied on a central coordinator node to prevent double spending attacks.
Which kind of raises concerns about decentralization.
Right, even though it was meant to be temporary. The sources also point out that transaction confirmation times in some DAG systems can be more variable compared to blockchains with predictable block times.
So that might not be ideal for all applications.
Right. It depends on the use case.
We see DAG technology being used in projects like IoT, which is focused on the Internet of Things, right?
Yes, enabling secure data and value transfer for IoT devices.
Then there's Hedera Hashgraph, which uses a form of Byzantine Fault Tolerance, but built on a DAG structure.
That's another interesting implementation.
And then Nano, which has this block lattice DAG where every account has its own blockchain.
Right, and transactions involve sending blocks between these individual chains.
So DAGs definitely offer this exciting vision of scalable, feeless transactions.
They do.
Now let's look at a truly novel approach. Proof of history, or PoH. This one isn't about how agreement is reached. It's about creating a record of the order and time of events within the blockchain itself.
PoH is a fascinating concept.
It is.
The core idea is that PoH creates a verifiable timestamp within the blockchain, which, when combined with other mechanisms, enables super high throughput.
Okay.
But it has its own complexities, especially regarding hardware, and it's not a standalone solution.
So how does it solve the problem of time in a decentralized system?
That's the ingenious part. Instead of relying on external timestamps, which can be unreliable, PoH uses something called a verifiable delay function, or VDF.
A VDF, okay.
It creates a cryptographic audit trail that proves a specific amount of time has passed between events. Basically, a leader generates a sequence of computations that take a certain amount of time to complete. And the results are cryptographically linked, creating a historical record that's very difficult to fake.
So it's like a tamper-proof timeline embedded in the blockchain itself.
Exactly. And this allows the network to verify the order of transactions without constantly relying on nodes to agree on timestamps.
Which can be a bottleneck, right?
Absolutely.
Yeah.
And the potential benefit is incredible transaction throughput.
The sources mention Solana as a prime example, achieving something like 65,000 transactions per second by using proof of history.
It's impressive. This verifiable time ordering also really streamlines the consensus process because nodes can be more confident in the sequence of events.
It sounds like a game changer for applications that demand really high performance and low latency, like decentralized exchanges or high-frequency trading.
Definitely. But the sources point out that implementing proof of history effectively does come with technical challenges.
Like what?
Well, validators often need specialized, powerful hardware to generate and verify these time-based proofs. And the cryptography behind it is quite complex.
So it's not a simple plug-and-play solution.
Not exactly. And it's important to understand that proof of history by itself doesn't provide consensus on the validity of transactions. It's primarily about establishing a reliable timeline.
So it needs to be paired with another consensus mechanism to achieve full agreement on the state of the blockchain.
Exactly. Like Solana, which uses Tower BFT, a variation of practical Byzantine Fault Tolerance, along with proof of history.
So PoH boosts speed and efficiency, but needs a partner for robustness and agreement on transaction validity.
That's a good way to put it.
Now, we're going to circle back to proof of authority briefly.
Okay.
We touched on the basics earlier, but it's worth highlighting its real-world use cases.
Definitely.
The examples of XDAI chain for stable payments and VeChain for supply chain management really show where proof of authority fits in.
Right. In those permissioned environments where trust is already established, sacrificing some decentralization for efficiency and speed makes sense.
It's a practical solution for specific needs, especially in consortium-based applications.
Absolutely.
All right, we've explored a bunch of individual consensus mechanisms, each with its own approach and trade-offs. But the sources suggest that the future might not be about finding a single best algorithm.
It's an interesting observation.
We're seeing this trend towards combining different approaches in hybrid and multi-layer solutions.
It's about leveraging the strengths of different algorithms, creating more robust and adaptable blockchain systems.
So it's like taking the best of each world and putting them together.
Exactly. Hybrid consensus models do just that. For instance, you've got Algorand's pure proof of stake, which uses a random selection process for block proposal and voting, or Polkadot's nominated proof of stake with its nominators and validators, and the Gram-TA finality gadget.
Right.
And then there's Casper CBC, which aims to provide formal guarantees of safety and liveness in a proof of stake setting.
So many different flavors.
Each fine-tuning the balance between security, performance, and decentralization.
Then we have layer 2 scaling solutions. How do those fit into this evolving consensus picture?
Layer 2 solutions offer a different approach to boosting performance. They build separate systems off-chain to handle transaction processing, periodically anchoring back to the main chain for security.
It's like creating express lanes to handle increased traffic.
That's a great analogy. They often employ their own consensus mechanisms off-chain, designed for high throughput and low fees.
So they take the load off the main chain, boosting scalability and lowering costs.
Exactly. And they still inherit the security of the underlying Layer 1 consensus. Popular techniques include optimistic rollups, ZK rollups, stake channels, and plasma.
So many options. So what's on the horizon for consensus mechanisms? What's the cutting edge?
There's a lot happening. We're seeing concepts like proof of space and time, or PoS-T, where participants allocate unused storage space to earn rewards.
So instead of just processing power, we're using storage capacity.
Exactly. Chia is a prominent example of that. And Space Mesh combines proof of space with proof of time, aiming for energy efficiency and using commodity hardware.
Interesting. What else is being explored?
Well, avalanche consensus is another big one. It uses a randomized sampling approach where nodes quickly reach consensus with very high probability.
So it's super fast and efficient.
Exactly. And then there's this growing interest in social consensus and governance where human decisions play a bigger role.
So bringing the human element back into blockchain.
Precisely. Projects like Tezos with its on-chain governance, Claros for dispute resolution, and Human Protocol for integrating human feedback into AI all explore this.
Now, we've covered a lot, and that classic blockchain trilemma of balancing security, scalability, and decentralization is always present.
Always a factor.
Our sources give a really good comparison of how these different consensus mechanisms stack up against those three aspects, as well as their energy efficiency and transaction finality times.
It's a helpful way to see the trade-offs. What becomes clear is that each mechanism represents a different set of design choices.
Right.
Proof of work is strong on security and decentralization, but struggles with energy efficiency and scalability. DPoS is efficient and fast, but might compromise on decentralization. DAGs offer high scalability, but have more complex security models. Proof of history can boost throughput, but needs another mechanism for full consensus.
It really highlights that there's no one-size-fits-all solution.
Exactly. The best choice depends entirely on the specific goals of the application.
And that brings us to the real-world challenges of actually implementing these mechanisms.
Right. It's not just theory. That trilemma presents real engineering hurdles.
It's about making those trade-offs in practice.
And then you have the complexities of validator economics. You need to design incentives that encourage participation and good behavior, but avoid problems like token inflation.
Right. You need to get those incentives right.
And you need robust slashing mechanisms to deter malicious activity without unfairly punishing honest mistakes.
So a delicate balance.
Absolutely. And then, as the blockchain ecosystem grows, achieving cross-chain interoperability becomes a huge challenge.
Trying to connect systems with different consensus mechanisms and finality guarantees is tough.
It's a major hurdle. So, looking ahead, what are the most promising future directions for consensus technology?
That's the big question.
One exciting area is adaptive consensus, where protocols can self-modify based on network conditions. Imagine networks that can dynamically adjust validator committees, fine-tune fees, or even ramp up security when attacks are detected.
So blockchain systems that can learn and adapt.
Exactly. And then there's the crucial focus on quantum resistance, researching post-quantum cryptography to protect against future quantum attacks.
That's essential for long-term security.
Absolutely. And then there's the intriguing concept of AI integration, using artificial intelligence to optimize networks, detect anomalies, and even potentially automate governance.
Wow, AI and blockchain. That's a powerful combination. So what's the key takeaway for our listeners from all of this?
I'd say it's the incredible diversity and the rapid pace of innovation in blockchain consensus mechanisms. There's so much more than just the basic algorithms. We're seeing a wave of new ideas, each with its own trade-offs, designed for specific needs within the decentralized ecosystem.
It's a fascinating and complex landscape. And as we've seen, there's no single best consensus mechanism.
The optimal choice depends entirely on the specific application and its priorities. Whether it's speed for decentralized finance, security for enterprise data, or energy efficiency for the Internet of Things, it's all about making those informed trade-offs.
And we're seeing this movement towards hybrid and layered solutions, combining the strengths of different mechanisms.
Right, it's about finding the best combinations for specific needs.
So as these advanced consensus mechanisms continue to evolve and become more widely used, it really begs the question, how will they shape not just the future of cryptocurrencies, but the entire future of decentralized technologies?
It's an important question to consider.
It's a topic worth exploring further, and we encourage you to dive deeper into any of the mechanisms that sparked your interest today.
The journey of decentralized consensus is far from over. These innovations are just the beginning of a truly transformative evolution.
Thanks for joining us on this deep dive.
It's been a pleasure.
Until next time.
See you then.
Thanks for watching Neural Blockchain. If you enjoyed this or not, let us know by leaving a comment or hitting the like button. Have a good one, and we hope to see you next time.